everyone to Ask the Experts. Today we're going to be talking about some of the latest developments in AI. I'm Tim Messagy, and I am joined by my AI expert, Rambus Fellow and Distinguished Inventor, Steve Woo. Welcome, Steve.
Hi, everyone. Thanks very much, Tim.
Great to have you here, Steve. Hey, to kick things off, why don't we talk about some of the latest developments in AI that you and your team are following?
Yeah, Tim, we're actually tracking a lot of really interesting things that are going on in AI right now, but probably one of the most exciting and most interesting is this new development in inference called chain of thought. It's really an improvement in the way some of these large language models operate, where very large and complex questions and prompts are broken down into simpler steps first to achieve kind of the answer to a more complex problem. And this really mimics human reasoning, where in order to kind of arrive at the answer to a complex problem, we take smaller steps and we reason through it. And so we're starting to see large language models and AI mimic that breaking down of larger problems into smaller steps during the inference process. And these multiple smaller steps allow us to arrive at a higher quality answer.
Steve, with chain of thought, are there implications for the hardware? Does it require more compute if you kind of stretch out the way that the model answers or thinks about the answer?
Yeah, it does actually. So this new kind of approach where we're breaking down large problems into smaller steps and then kind of following a logical progression in those steps. What we're seeing is that these steps each take their own amount of compute power, and kind
Right.
of reasoning through in multiple steps is taking more kind of compute capability to arrive at a higher quality answer.
And as it takes each of these steps, does it like check in with the model? How does it do that, reasoning process?
Yeah, there's a couple of different ways where the models can, take their own answers and then infer yet again in the next step from that answer. There
Kind
are
of iterating.
ways, yeah, and there are also ways of doing iterative prompting where you can actually take intermediate steps to check the results, even refine it, and then ask ensuing questions to refine and kind of mimic that same process. But the power of chain of thought is not necessarily having to have a human kind of in the middle there. So,
Exactly.
yeah, so the goal is really, can the model do this all itself? But there are still ways to kind of check in on each of the steps as the models are generating intermediate results.
So, Steve, chain of thought puts even more bandwidth and capacity pressure on the computing architecture. Um, what innovations can we use to get more of that to, feed this voracious need?
Yeah, it's a really good question, Tim. It's something that's been driving a lot of the direction of the industry for the past 5 to 7 years, and it's going to continue to drive it going forward. Some of the different ways that we provide more memory bandwidth and capacity, probably one of the prime examples is with HBM and stacking. We take multiple die and we stack them together in the same package, and we use that stacked architecture to get more bits in this in a kind of a larger capacity in the same footprint. And we have a lot of wires that go between the HBM memory device and the processor. And so having a lot of wires means you can get a lot of bandwidth. Now, there's always a desire for more. And so the industry is looking at stacking even higher. And then, in addition to adding more wires, we're looking at figuring out how to signal faster across those wires. And so, increasing the data rate, that can take different forms. In the case of HBM, it's simply just running the wires at a faster data rate. If you look at other technologies like GDDR, for example, in addition to going at higher data rates, they're also going to multi-level signaling. So having multiple voltage levels, in this case, in GDDR7, there's 3 voltage levels. So we can actually communicate more information in each particular bit time. And so those are a couple of different ways. Now, there's another technology that we're seeing that will be coming out soon called MRDIMM, or basically it's the ability to multiplex between different ranks of DRAMs on a module. So the simple way to think about it is on DIMM modules today, you have some DRAMs that are on the front of the module, and you have some DRAMs on the back of the module. It turns out that only a subset of those DRAMs today can ever be transmitting on the wires between the memory module and the host. And so the idea is to allow all the DRAMs at the same time to be transmitting on those same wires to and from the host. And the way we do it is we take those independent subsets and we basically multiplex their data transmission onto the same wires. So you might have the DRAMs capable of transmitting at one data rate X, gigabits per second. But when you multiplex two different independent sets of DRAMs, you're actually transmitting at 2X back to the host. And the way we do that is we have an additional set of chips on the module that buffer these two independent streams of data, and they multiplex at twice the data rate back to the host. So this is really just another way of trying to get the devices that are, maybe are sharing the wires and to allow them to transmit at the same time. Again, we're able to get higher bandwidth by doing that. And so the industry is coming up with a number of different ways to be able to increase the capacity and the bandwidth, just like some of these ways that I've just mentioned.
So, Steve, in parallel with the greater demands for more and more performance, either bandwidth or capacity, we're also seeing tremendous rise in the requirements for greater power as we scale up and scale out. What are your thoughts on managing the power budget?
Yeah, Tim, that's really an interesting area right now that we're seeing in the engineering of AI systems, really in all systems in general. So what we're seeing is that power is no longer scaling like it used to back 10, 15 years ago. And so as these systems are doing more work, we're actually seeing that they're consuming more power. And it's becoming difficult in two ways. One is, how do we cool these systems? The other is, how do we even supply power into this volume where all these components are trying to consume much more power? Just to give you an idea, some of the latest systems that have been announced by NVIDIA, they're increasing the power in the racks by close to a factor of five. And so, now you've got 5 times the power that you need to dissipate and cool. You also have 5 times the power that you need to deliver into the system. So the path to cooling turns out the AI infrastructure has been switching over to liquid cooling. And the capacity of absorbing and removing heat, the capacity that liquids have to transfer and move that heat is much, much higher than air. And so the industry has a path now to cool these systems simply by using liquid. And so we're starting to see that transition, and we expect to see that transition become kind of a standard thing in the future. The other part of the problem that I mentioned is, how do we even power the components to begin with? And it turns out that if you don't do anything to the voltage, simply increasing the amount of power means the amount of current that you need to supply has to go up. And it turns out that with the copper wire and the infrastructure that's there today, past a certain point, you'll start to melt those wires. And so the way to kind of manage this, to keep the amount of current manageable, is to increase the voltage. And so we're seeing a shift from the standard 12-volt infrastructure to 48-volt infrastructure, and that effectively reduces the current that you need by a factor of 4 because you've increased the voltage by a factor of 4. Now, as we consume more and more power going forward, there will be a desire to increase the voltage even higher than 48 volts. And we're seeing discussions now of and initial work in areas as high as 400-volt infrastructure, just to kind of keep the current manageable and to allow the existing copper wires and infrastructure that's there today to continue to be used. Now, the challenge is that when you're delivering much higher voltages into the chassis, just to manage that current, you do eventually have to step it down to the voltage that the silicon components want. And today, a lot of the components want voltages that are around 1 volt or zero point 0.9 or zero point 0.8 volts. And so there's an additional power conversion step between the much higher voltages down to the voltages that the components want to use. So there's going to be some changes that are going on in the infrastructure and certainly in power management and power delivery. And so we see, two really interesting kind of changes going on. One is in the cooling, moving to liquid cooling, and then one is changes in power delivery and power management that are going to be critical going forward.
So, Steve, with these, kind of very dramatic changes in the power delivery system, what are some of the implications for semiconductor components, specifically, power management ICs, PMICs?
Yeah, it's a great question. So I mentioned that, these changes in voltage are happening, and we do need to convert the voltage from, one level that you're shipping it around the data center and into the
Right.
chassis to what the components need. And so what we're seeing is we're seeing greater need for these ICs called power management ICs or PMICs. The idea is that the PMIC provides the conversion, and you want to
Yes.
do that conversion very close to the components that consume that other voltage. The reason why is that the longer you have to move, your power, the more you can lose energy. And so doing that conversion close to those components means you'll have the highest quality and you'll have the fewest losses as well.
Okay.
So really, what we've seen in the DDR world is DDR5 DIMMs now include a PMIC so that we can have high quality power at the DRAMs. And with the changes in the kind of the voltage levels and the number of components that are being put together into these smaller volumes to get more performance, we're expecting to see PMICs show up in more places. And the PMICs will be supporting larger numbers of kind of voltage conversions as well. So we expect to see basically a growth in the amount of PMIC silicon that's going to be in these chassis.
Okay. Great. Great. So final question, and to take a step back. AI is just a game-changing technology, and when we've had game changers of this magnitude in the past, it's brought in all sorts of new use cases, new applications. What are some of the, compelling use cases that you're following?
Yeah, I mean, you're right, Tim. I mean, we've seen, over the years, really big game changers like the internet, for example, and that
Right.
brought about new business models for e-commerce. We saw cell phones allowed mobile computing, and now you're able to, to kind of have really good connectivity and really good applications for things like navigation and even just simple information lookup. With AI, there's a number of things that we're seeing that can be really killer apps or big game
Yeah.
changers. One of them is simply just the large language models, what we're seeing today, just that
Hmm.
ability to answer complex questions and to be able to synthesize and summarize information like we're seeing today. We expect that to get better.
Yeah.
These things like chain of thought reasoning and other new techniques that people are working on, we're seeing generation to generation, the accuracy is going way up. Another
Exactly.
area that we're seeing that is very, very interesting and compelling is robotics. And
Mm.
so just being able to train robots to navigate in the world and to do tasks. We're able to create digital twins, basically virtual worlds that we can train these robots in at much faster speed than we could train them in the natural world. And
Hmm.
that allows
Hmm.
us to, to be able to contemplate environments that are difficult to mimic or expensive to mimic. And that we can train these devices to do things that can basically help humans. So it's the assistive kind of technologies and the ways that we can make humans more productive. So what we've seen is anytime you have a new technology like the internet or mobile computing, whatever, that makes humans more productive, those tend to take off and they tend to open up new possibilities for yet further improvements in technology. And we're expecting to see, all those kinds of things happen as well in the future with AI.
I couldn't agree more. A very positive future. Steve, thank you so much for your time. And everybody, thank you for joining us. We'll see you again real soon here on Ask the Experts.
Thanks,
Thanks
everyone.
again.